Hello everyone. Hi. Am I audible clearly to you guys? Just let me know in the chat. So hi guys, hi, how are you? So those who saw me in the previous session, welcome back to channel again. And those who are new, welcome back. Welcome, not back, welcome to the channel and hope this community, Let's Upgrade community helps you a lot. So just let me know in the comment section. I'm reading your all the comments over here, so just let me know in the comment section that I'm audible all loud and clearly, so I can see like there were so many questions already asked in the comments. I'll give you the answers of all the questions regarding the certificate and all. And but before that, just confirm me that I am clearly audible. Yes. Great. So, hi guys, let me introduce myself. This is Harshad C. Solanki. I work here as lead of operations, and we have Amulya ma'am with us. So, she is going to be your instructor for data structures and algorithm. So, before moving to that, are you guys excited? Just let me know in the comment. Are you guys excited for this course? Yes. Sahi. So, are you guys excited? Agar excited, so mark OP, let's say data structure OP in the comment section. Great. Okay, guys. So where are you from, guys? Just let me know in the comments after this OP is done. Great. So where are you? Where are you from? So, ma'am, where are you from right now? Ma'am, am I audible? Great. This chat. Ma'am, am I audible? Hello? Jharkhand, Mumbai, Kolkata, Pune, Ahmedabad, Assam, Lucknow, Hubli,
Hello?
Nats.
Yes.
Yes, ma'am. So I was just asking, like, where are
Hello?
you
Am I
live
audible?
from? Yes, ma'am. You're audible. Hello. Okay, Tamil Nadu, Sikkim, Amritsar.
Okay,
Yogi.
I'm live from I'm live from Bangalore currently. Yeah.
Great. So I am from Mumbai. There is one guy, Yogesh, who is from Mars. So welcome, Yogesh. So yes. Great, guys. Great. So we all are from different regions of the country, and we can be a friend. We can be a, like, it's our community. We can network. We can talk. We can learn. So that is what learn, build, share, grow it is. And not taking you much time, we'll move ahead. So I'll give you quick few instructions. So before the instruction, as I said in the previous session also, check in the comment section that your best friends are there in the chat. बिकॉज हम क्लास में जाते हैं तो ऑब्वियसली वी फाइंड आउट लाइक वी वांट आवर बेस्ट फ्रेंड्स टुगेदर, राइट? So if they are not, go and share the link, bring them in the chat, be with them, study with them, and yes, we'll take this ahead. So I'll quickly give you few instructions. So there are two instructions which I need to give, and then I'll hand it over to Amalia ma'am. Okay. So the very first instruction is register the course. If you have not registered yet, go and register on our website. So all the links will be there in the description. Okay. So if you are watching from the mobile, there will be an arrow if you can't find the description, and if you are watching from the web, there will be show more options below this video. So go and check out the description box. You'll get all the details over there regarding the course. Okay. So the very first is registration is important because the second instruction is dependent on the registration. Okay, so if you don't have registration, you'll not get certificates. Talking about certificates, now we give two types of certificates. Okay, so one is participation certificate and one is completion certificate. What is participant certificate is, yes, there is an attendance. You need to mark daily attendance. So you will be having this 3 days of classes. You need to mark attendance daily. Okay, and let's say you didn't submitted your assignments or project, then you will get the participant certificate. Okay, and in case with the attendance, you have submitted all your assignments, you have submitted all your project which will be given by Amelia ma'am, then you will be getting completion certificates. So what next of completion certificate is, yes, you will get hard copy delivered at your home. So once you go further with the process, with the course, we will guide you. We will take your all the documents and like address and everything, details and all, and we'll deliver your hard copy. So only condition is mark all your attendance, submit all your assignments, submit all your projects, and you will get your certificate. Okay, so am I clear, guys? Am I clear with the registration? Am I clear with the participant certification? And am I clear with the uh, whole completion certification? So there were a few questions, ma'am, which was asked by the students. So they were asking about the prerequisite and all. So later when I'll give you a handover, you can just guide them about the prerequisite for this course and everything. So before that, just give me something confirmation that I'm clear and we can go ahead. Where to mark attendance? Yes, links are there in the description. It will be there given by the mods in the comments also. So there are mods who will be helping you.
Yeah,
We
yeah,
welcome
sure.
you.
Yes, of course.
Yes, ma'am. Yes, ma'am. So there are mods in the comment section who will be helping you. Amulya ma'am is here. Grab all the knowledge what you want. Okay. And in case, ma'am, you need any help, you can call up our mods and they'll be here. So yes, great. Okay, guys. So as you made it very clear that I'm clear, then I'll leave. I'll leave you for the class. Hope you enjoy it. All the very best, ma'am. All the very best, students. Oh, this community
Okay.
is what we are building, and you'll love it. So again, bring your networks, build your networks, learn, build, share, and grow. Okay, guys. So bye bye. Take care. Yes, ma'am. Over to you and mods.
Yeah.
Can
Thanks
you
a lot,
take?
Harsh. Thank you for your introductory yeah thing to us. So yeah, hello everyone. Very warm good evening to all of you, and welcome to my session on the data structures and algorithms day one session. Okay, so are you all excited to learn the course? So the prerequisite, as you all have asked, I think some of you had this question also. Most of you have this question in your mind. So prerequisite is you just have to know the basics of C or C++ programming language. Yeah, so you need not know in depth all the concepts or all the concepts associated with either C++ or be it C programming language as well. Just the basics would be sufficient for you to know. You just have to know what is pointer, what is how does the loop actually executes, what are the basics of arrays, functions, and pointers and stuff. So if these concepts are clear to you, and yeah, so I think that would be great. Okay, so shall we start with the today's session? Yeah. Okay, so I'll share my screen. I'll share my desktop. It's okay. Uh, yeah, just let me know once the screen is visible for you or the presentation is visible for you. Okay. So are you guys can see my screen, right? Okay, yeah, great. So yeah, okay. So maybe I'll put it in a full screen mode so that yeah, so it is visible very clear and in a better way. Okay. So today we are going to start with the fundamentals of time complexity. So that is the agenda. Okay. So of what exactly is time complexity of an algorithm, and the details of how can we actually try to calculate time complexity. What exactly is this time complexity, right? So how do we start with this concept to begin with, right? So we have heard this multiple times with the people talking about, okay, when you write an algorithm, what is its time complexity, what do you mean by when how can you minimize the algorithm so that the time complexity reduces, and so on. So you might have heard this all these terms multiple times, right? So today we are going to talk about just the time complexity part and the related parameters or the associated terms with us, and how can we actually calculate the time complexity parameter. Okay, so shall we start with the today's session? Okay, so to know how do we calculate the time complexity, first of all, we have to know how to write an algorithm. So what is an algorithm basically? So algorithm is, as everyone knows, so algorithm is a finite set of instructions that are carried in a specific order to perform a specific task, right? So as highlighted in the bold term, so it should have a finite set of instructions. So the instructions have to be finite in number. It shouldn't get stuck in any infinite loop or any infinite parameter being read, and so on. So it has to carry out a finite set of instructions, and it has to be in a specific order. Okay, so one after the other. So in what order that needs to be carried out is also, it really matters. So I think you have a hands-on programming experience also. So if at all you try to use a variable before its declaration, so that is not a right order of carrying out a certain programming code, right? So and it has to perform a specific task, right? So you have to ultimately achieve something out of whatever you try to write the program or you try to write the code, right? So that is nothing but an algorithm. So an algorithm is, it has to have finite number of instructions in order to carry out a specific task, and it has to be in a specific order. Okay, so these are in simple words how can we define an algorithm. So it will typically have the following characteristics as well. So inputs is, it will have zero or more input values. So it might take no input values as well. So in that case you will not have any input parameters for that function or for that algorithm, right? So or you can have multiple inputs as well, and outputs also, you can have one or more outputs, right? So at least it should give one specific output so that you can achieve whatever you were trying to actually aiming for, right? So that is nothing but an algorithm, right? So it has to be unambiguous in nature, right? So it should have very clear and simple instructions to carry out the steps, right? So it should not create into any unambiguity. So it should have very clear and simple instructions. Okay, and finiteness, yes, there should be limited number of instructions. So as I said, finite number of instructions, right? So there should be a limited number of instructions to carry out the job. Okay, And then effectiveness, so each instruction has an impact on the overall process, right? So how effective is your code? So if you go on just writing thousands and thousands of lines of code, and without have intending to not to if you don't achieve anything ultimately out of whatever you try to write, so then that is not very effective, right? So you should really be your algorithm design should be in such a way that it has to be very effective manner, it has to be very optimum in nature, right? You have to minimize as much as the lines of code or whatever the program that you write or the program that you try to design, you have to minimize as much as possible, right? So that is nothing but these are some of the following characteristics of the algorithms. Okay. Yeah. So typically an algorithm, it would look something like this. So say we are trying to compute sum of two variables, right? So this is just a simple example of one can think of, as soon as you try to write a function or you try to write a program or yeah, and so on, right? So how does an algorithm actually look like? So it is again a step-by-step process itself. So the first step is obviously start of the program. So usually in your C or C++ programming language, it is int main, right? So that is where your program would begin its execution, right? So the start, soon after the start step, that is your first step of the algorithm, you try to declare the necessary variables. So what are the variables that are required to achieve addition of two numbers? So you should have two basic integer numbers, and then to hold the result as well, you need to have a separate variable, right? So we have taken three variables here. Then the next step is you try to read these variables num1 and num2 from the user, right? So if at all you try to carry out the job using the numbers that you try to read it from the user, then that becomes your third step, right? So the fourth step is you try to carry out the sum and assign it to the assign the result to the sum, okay? And then the fifth step, display the sum. So whatever the result that you would have got, you have to display it onto the console window, right? And the final step is nothing but the stop. So there has to be a stop, there has to be the terminating statement that really is required, right? So the program should not be abruptly ended, right? So it has to be necessarily it so if it is C++, you have to have a return statement in case of main function, because it is int main, so it is designed in such a way that it has to return an integer variable. So that is why we have written 0 at the end of the program, right? So that is nothing but the stop. So that is where you try to return from the main function. So that is where your program actually ends. Okay. Okay. So now once you have written the algorithm or once you have designed your program, so what is the next step that you try to carry out? So what is algorithm analysis, right? So how do you actually try to compute how much time is it required, how much space does your algorithm take? So that is what your analysis is mainly carried out. Okay. So, algorithm analysis is a study to provide the theoretical estimation for the required resources of an algorithm to solve a specific computational problem, that is calculating efficiencies, right? So, say suppose you have a problem statement given to you, okay? So that is why you have multiple approaches in order to solve that problem, right? So now, how do you actually compare multiple approaches that you yourself has designed, or say various users have designed in actually solving that problem? So how do you actually compare with each other, right? So how do you know that which one is actually good, which one is actually better, or which one is actually more efficient, right? So there has to be necessary parameters for the comparison, right? Okay, so that is where the analysis or the efficiency comes into the picture, right? So efficiency of an algorithm is related to the input length known as time complexity, or the volume of memory known as the space complexity. Okay, so there are two parameters or the two bases on which an algorithm is actually compared with. Okay, so these two bases are nothing but the input length and the memory that is being consumed by the CPU. Okay, so the time that is, say for example, if you have a Trivago app or some app on your mobile phone, and you try to sort some you try to list down you try to purchase something. So say for example a television, so you try to search for smart TVs in your Flipkart or Amazon, and then you try to sort it, or you try to filter it according to your requirements, right? So you try to sort it either in increasing order of the rate, right? So it begins with as lowest budget that you have, that you can have as say 9,000 or 10,000. So that is where your basic models actually comes into picture. So 10,000, 12,000, 14,000, 15,000, and so on. So that is how your Amazon app or your Flipkart app tries to sort whatever products it has, okay, in their stock. They will try to sort it. Okay, so in that algorithm, the particular sorting technique, what if it takes infinite time? Will you be able to be patient enough to actually wait for 15 minutes, 20 minutes, or how long can you keep waiting, right? So nobody has time as a in these quick running days, right? So time is an important parameter, so you have to fetch the results as fast as possible. So that is where your time constraints actually comes into the picture, right? So I hope you got an example, or you got an idea of how the time complexity is calculated. So why the time complexity parameter is really very important in designing an algorithm, right? So everyone tries to only specifically specifically look at this time complexity parameter as compared to the space complexity. Of course, space also really does matter, but we will see what exactly is space complexity, and why is it not of that importance as that of the time complexity. Okay, so as I said, what is the need of analysis? So generally there are multiple approaches, and in order to actually compare with each other, so we actually have derived two bases, that is nothing but the time and the space. Okay. Okay, so what does a better algorithm mean? So there are multiple criteria actually. So faster, less memory, or easy to read, less lines of code, or less hardware or software that is required, right? So whenever we are trying to calculates its efficiency, how efficient an algorithm is, we are not giving exact values, right? So we are not trying to achieve exactly at what instant of time can we obtain the results. No, that is not the ultimate goal. Okay, so we are roughly trying to give a figure how the algorithm can depend on, or how on what degree of the input variable can it actually depend on. Okay, because your input actually parameter really varies with respect to at different instance of time, right? So depending on the situation, it usually varies, right? So depending on the input parameter itself, how your algorithm is mathematically be related to, or yeah, we try to derive the time complexity out of that. Okay. Okay, so let me give an example of time complexity of an algorithm. So what is the rate of growth? So as I said, the number of inputs n increases, that really matters. Okay, at what rate the complexity increases is nothing but the time complexity parameter. Okay, so consider here we have an example of computing the sum of n variables or n numbers. Okay, so what is the input that you take? It is nothing but the integer n. So n will indicate the number of the integer number up to which you try to calculate the sum, right? So here I've considered a for loop, and up until n, from 1 to n, I try to compute the sum. So I have initialized the integer sum with 0, and I just run a for loop, a simple for loop from 1 to n. I go on computing the sum. Okay, so here you can see that I am taking a loop, and when I pass, say n is equal to 5, for example, so how many times I am trying to run the statement actually, right? So here the for loop actually, the initialization is done once. Okay, so int I is equal to 1, it is just once. So this statement will be executed just once. And this statement, can you just tell me how many times will it get executed? Yeah. So the comparison will be done right from the beginning, whether 1 is less than or equal to n that you have passed. So n I have taken as 5, right? So 5, 1 is less than or equal to 5. Yes, the condition satisfies. So it enters into the loop, right? So then it computes the sum is equal to sum plus I. Okay, so my sum is 0. So 0 plus 1 is nothing but 1, right? So then I plus plus, it tries to increment the iterator, right? So I is nothing but the iterator in my for loop, right? So it tries to increment the iterator. So you can see that so I plus plus will be evaluated exactly 5 times. So the first time it will change from 0 to 1, second time it will change from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, right? So these, the number of times the I plus plus gets executed is nothing but n plus 1 times. Okay, whereas I is less than or equal to n, comparisons will be done n plus 2 times, right? So right from the beginning until you have reached I plus plus, that is the condition actually is not met, that is when I turns to 6, say in this example. So n is 5, so up until 5 it runs, everything is fine. Okay, so when it turns to 6, an extra comparison has to be done, has to be carried out, right? So that is where the comparison statement is always one ahead of your iteration statement, or the number of statements inside the loop, for loop, that will be carried out. Okay, but yeah, this is just an information, or this will not really matter in terms of calculation. But what really matters is inside my for loop, whatever statement, set of statements I have, how many times will it get executed. Okay, so say this instruction will take how many ever cycles. Okay, so say 10 microseconds or 20 microseconds. Okay, this statement will take 20 microseconds to get executed. But when I pass for a large number of n, so from 5, if I modify it to 100, how many times will this statement gets executed in terms of time parameter, right? So it will go on increasing with respect to the n value, right? So if I pass, instead of 100, if I pass 1000, if I pass, instead of 1000, whatever maximum value that an integer variable can really hold, if I pass that, then you can imagine, right? So what will be the timing parameter, or what will be the time taken in order to, for you to compute this for loop itself, will be comparatively bigger, right? Right, so you can just imagine what will be the time complexity of this algorithm one. But instead, now if I know the direct formula which will fetch me the sum of n integers, right? So mathematically we know that sum of n integers is actually, we have a standard formula which is n into n plus 1 divided by 2. What if, so okay, now I've taken n is equal to 5. So how much time will it take to execute this single instruction? So as I said, I had taken an example of say 10 microsecond. What if the n value gets increased from 5 to 100? What will be the time? It will remain constant, right? So it will remain still 10 microsecond itself, because it is just a single instruction. I am not repeating it again and again, right? So I am not iterating it, or I am not calling it recursively, or I would rather say put it iterative manner itself. So I am not iterating the statement again and again, but rather I am just executing it once, right? So which is why it is a constant behavior. So whatever input size that I give, the steps is fixed, right? So you will have a constant behavior, so which is why we call it as a constant time parameter. So this will take a constant time in actually computing this algorithm, right? So this is the difference, main difference between the algorithm 1 and algorithm 2, how I have designed. So this actually linearly increases with the increase in the number of inputs, but this will have a constant behavior with whatever input I have with of integer n, value of n, right? Okay, so I hope this is clear to you, with this simple example of how the time complexity actually is, it really matters with respect to the design of algorithm. Okay, so shall we see now the space complexity? What exactly is the space complexity? So for any algorithm, memory is required, of course, right? So in order to store the local variables, in order to store the global variables, in order to store various program instructions. So we have that format. I hope you are very aware of where the code actually code segment resides, the data segment resides, and stack, heap. So there are various segments of memory, how a memory is actually segmented in a program, right? So the lowest possible program memory has the code segment, which where your program instructions are actually stored, right? So that is where your memory is really required in order to actually store the program. So it will have various things to actually store. So you will store the constant values, you will store local variable values, and if at all during execution, during the runtime, if there are multiple function calls or there are multiple jumping statements, you have to actually try to store the address of the current instructions that you're trying to execute as well, so that you can jump to the next function where that function will be called next, right? So these are some of the the parameters where you can think of where the memory will be consumed by a program, right? So the space complexity is actually calculated with the input space plus the auxiliary space. So what do I mean by auxiliary space now? So input space is constant because once you have designed a function, so say you have two numbers. So as I had given an example of addition of carrying out an addition of two numbers or two integers. So I'll take two numbers, so two integer variables and a result variable, that is integer variable, to store the result. So there will be three variables of type integer. So I know what will be the total size taken in the memory. That is nothing but the 12 bytes. So if I say integer variable is, each integer variable is of 4 bytes. So three variables I have declared, which will give me ultimately 12 bytes. So I know that 12 bytes of memory is required whenever that function is being called, right? So 12 bytes of local memory. So well, local memory, I mean local variables values will be stored in the stack itself, right? So that is where the my 12 bytes of memory will be consumed, right? So my input space is constant for a given function, right? So input space does not vary whenever a function is designed or whenever an algorithm is designed, but what varies is nothing but the auxiliary space. Now what do I mean by this auxiliary space? So auxiliary space is nothing but temporary space excluding the input size allocated by your algorithm to solve the problem with respect to the input size. So see, suppose you have a recursive function call. Okay, so I'll take an example. I'll just jump to the example of what I have with me. So I'm trying to calculate the factorial of a number, right? So the first approach that I can think of is nothing but using a for loop, right? So for using a for loop, I just know that I have to have an integer variable factorial in order to compute or store the result of that fact number, and input variable parameter that I get n is from the function call itself, right? So and then I have to have an integer variable iterative in order to carry out the a repeated multiplication until I reach that number n, right? So now I know that I just need 8 bytes of memory, right? So 4 bytes of memory for integer fact variable and 4 more bytes for that integer iterative variable, right? So my input size is fixed here, and there is no auxiliary space at all that will be consumed by this algorithm one that I have designed, right? So auxiliary space comes into the picture if at all you have iterative function calls. So what do I mean by this? So now in my algorithm 2, what I have considered is I have considered a recursive function call. So recursive function call, I think you are very well aware of, right? So a function which calls itself with, again, the self-calling function is nothing but the recursive function call, but there has to be a terminating condition or a base case which terminates that recursive call as well, right? So otherwise it just goes to an infinite function call, and then you will be stuck executing the same function again and again and again, and your stack memory overflows, right? So this, I hope you are aware of what is stack overflow, what is the base criteria in order to actually cut down that recursive function call and so on, right? Okay, so in this recursive function call, so here as soon as you see the program, what is the input parameter or what is the input space designed in this factorial function? Absolutely nothing. I've not taken any local variables at all, right? So I've not, the whatever the n value that I'm getting, it is via the input parameter through this function call, but I'm not having any local variables at all, right? So the input parameters or the input space for this algorithm is absolutely zero, but I have the auxiliary space. Now, what do I mean by this, right? So if say suppose n value is apart from 1, I have passed say 5 or 6 or any other different value, right? So suppose I have passed 5, okay, so it comes to the else part during the first call, right? So it will try to return 5 into factorial of n minus 1. So when I see 5 into, I try to recursively call the same function, it will store the current execution in the memory, right, in the stack memory, and then it will again recursively call the next function, that is fact of n minus 1, so fact of 4, right? So this instruction where that 5 into 5 multiplied by the next function call was being executed, it will be stored in your memory, in your stack memory, right? So again during the next function call, when you try to manipulate this 4 multiplied by the next fact of 3, that statement also will be again stored in the stack memory because you have a function call again, right? So each and every time you have a function call, the current statement execution will be stored in the memory. I hope this concept you know it, right? So as soon as you have a function call, whatever current statement that you were executing, it will be stored in the memory, and then you go to that function wherever whichever function is being called, and then you try to execute those instructions, right? So that is how your function call really works, right? So in case of the recursive call, you will go on storing the program execution wherever it was being halted, or wherever it was tried to call the self, it will try to call itself, right? So multiple times. So now you can think of how many times this algorithm will go on storing the execution, the program execution, again and again and again, so recursively, right? So it will go on pushing the current program execution address, right, onto the memory, onto the stack memory, and until your base condition or your terminating condition is achieved, right? So the space complexity will go on increasing linearly with the input parameter n. So say n is equal to 5, I had 5 calls, function calls, recursively, iteratively, right? So you will go on pushing 5 times the current execution wherever it will be halted, right? So suppose from 5 I increase it to 10, right? So you will have to recursively call the function itself 10 times now, right? So now the you can imagine the memory or the stack memory space that will be consumed in order to actually store the current execution or the program instruction where that recursive call go on keeps happening, right? So this is how I can try to differentiate between the space complexity with the algorithm 1 that I have and with the algorithm 2 that I have taken as an example. Okay, so far anyone has any doubts? Okay, so we will try to see what is asymptotic algorithm analysis. So we will just try to briefly look into the different aspects that we have. So a method of defining the mathematical boundaries of its runtime performance. So asymptotic algorithm analysis is usually taken for the time complexity. It is taken for the space complexity as well, but it is usually referred to the time complexity parameter itself. So we have three different notations: big O notation, big omega notation, and big theta notation. Okay, so big O is nothing but the worst case scenario. So the slowest time that your algorithm can ever take, right? So it will actually depend on the input parameter or if else conditions, if at all you have in your algorithm, right? Right, so if you have your if condition, so in this previous algorithm itself, so if at all the value of n is equal to 1, it will not take much time. So that is your best case, so that is your fastest execution ever that you can achieve with the result, right? So if at all you pass n is equal to 1, you will be able to get the result in no time. So that is the quickest possible or the fastest solution that you can take. So that is nothing but the best case. What will be the worst case? Worst case is nothing but as big as you can think of the value of n, right? So that is nothing but the worst case or the slowest time taken ever for that algorithm to be computed, right? So it is also nothing but it gives the tightest upper bound or maximum possible n steps that is required in order to compute the algorithm, right? So big omega notation is nothing but the best case or the fastest time taken ever. So as I said, n is equal to 1, you will get the fastest ever result that you can think of, right? So as compared to n is equal to 5 in computing the factorial, if at all you give n is equal to 1, it will be fastest, it will be quickest in time, right? So that is nothing but the tightest lower bound. Okay, so minimum possible n steps that will be required by your algorithm, right? So big theta is nothing but it describes the average case scenario. So when best case and worst case are the same, that is nothing but your average case. So average of the best case and the worst case will give you the theta notation. Okay, so these are the three notations that we have, but usually we go for big O notation because what, so say suppose you have you go to a tailor. Okay, so you try to give your whatever you try to you want to wear for upcoming fest or something. Okay, so you will ask the tailor what is the best time or what is the fastest that you can actually stitch it and give it to me. Okay, so the tailor will actually give you so many constraints like, okay, I have so many orders now, I have to serve so many people, I am overtime working and so on and so forth. But you will ultimately try to ask him what is the best possible earliest time that you can actually have the dress with you so that you can wear it at the for your festival that will be nearing to you, right? So that is nothing but your best case scenario, right? So the worst case scenario is nothing but, okay, if at all, is it possible like tomorrow night or tomorrow day after tomorrow morning, right? So these are the possibilities that you can think of. So that will be the worst case, right? So a worst case is nothing but, okay, tomorrow if you cannot give, is it possible like day after tomorrow? So you will go on thinking of the possibilities, right? So that will be the worst case. So average case is nothing but, so average time or typical that tailor will actually take. So average time is like, okay, if at all there is no fest or there are no actually loads with respect to the tailor, he will give you it in 2 to 3 days. He will stitch it and give you it in 2 to 3 days. So that is nothing but your average case scenario, right? So these are the three possible notations that is same applicable for the algorithm as well. Okay. So now how to find the big O notation? So how to compute this big O notation? So you will have to consider the fastest growing variable term. So you will have multiple input parameters, no doubt, for your algorithm, right? So whichever is growing very fast with respect to the input parameter, so that is the variable that you have to really consider. Okay, and then you have to eliminate the coefficients and the constant terms also. Okay, because you know that with respect to the input parameter, when you're trying to actually compute, the other parameters will remain constant, right? So whatever coefficients it is associated with, or whatever think of you can think of a constant which is being divided or which is being multiplied, right? So all these will remain constant. So constant terms also will remain, you just have to add it or you just have to subtract it. It really doesn't matter with respect to the variable that you are trying to consider. Okay, so what really matters is nothing but the degree of the input variable. So what degree it is, whether it is a quadratic, it is a polynomial, or it is cubic, or it is exponentially increasing, and so on. So these are some of the common asymptotic notations, right? So if at all it takes a constant time, we actually denote it with the O of n. So if it is logarithmically increasing, it will, we will say that it is O of log n. So note that when we say logarithmic complexity, it is always with respect to base 2, right? So base is always 2. Okay, and linear complexity, so as I had given a couple of examples in case of time complexity and space complexity, so it will linearly increase with respect to the input parameter n, right? So logarithmic linear is nothing but n log n, right? So quadratic is O of n square. So these are some of the examples that I have actually picked. We will see a short code snippet also, which will lead to these time complexities. Okay, so cubic of n cube, and then exponential is it will grow exponentially very for a tiny small increase in the n variable value also, it will have a big impact in your code. It will have a big impact in the timing parameter as well, right? So note that one is the least possible constant, a constant time is the least possible time that you can actually consume in, that you can, that an algorithm can take, followed by log n, and then comes the square root of n, and then it is linear n variable, then followed by n log n square, n cube, and so on up till n raised to n. Okay, so this is the quick short introductory introduction to the deco notation. So now we shall consider the different scenarios or the different code snippets where we will try to find the time time complexities. Okay, so far anyone has any doubts? Yeah. Too fast to understand. Okay. Okay. So yeah, I just let me know whichever part is kind of is a little unclear for you. See, I have taken multiple, actually, various concepts, so which is why I have actually quite rushed to finding calculation of the time complexity is what really matters, right? So that is why the theoretical concepts or the introductory concepts were like, uh, I just took it a little fast, right? So I'll try to explain in depth whenever we try to consider the code snippets. Okay. Okay, so getting this PPT, I will try to circulate this presentation as soon as the session is done, so you will have the PPT with you. Okay. Okay, yeah. So, shall we start? So now we will try to see different code snippets and how can we then try to calculate the time complexity for them. Okay. Yeah. I'll try to sum up everything at the end of the session briefly. Okay. Right. Okay. So are you guys ready? Right. So shall we start? Okay. So first, find what is the time complexity of the below code snippet. So first, I have taken an example, a very simple example of a for loop. Okay, so this for loop, I am iterating it from 0 to n, and I am just having a simple statement of displaying hello onto the output console output, right? So what will be the time complexity? Time complexity is nothing but how many times will this statement get executed, right, with respect to the n parameter. So what will be the time complexity of this? Yeah. So please try to quickly answer in the chat window, right? O of n, O of n, O of n. Yeah. So everyone is actually, most of you have answered it correctly. So it is O of n because n is the parameter that is varying here, right? So this statement will get executed n times from 0 to n, right? So it is ideally 0 to n minus 1, but since I have considered 0 here, it is ideally n times, right? Okay. So next. So now I have, uh, 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 slightly changed this loop. So I have initialized it with the n, and then I'm decrementing the iterator I minus minus, and again the same statement is being executed. So what will be the time complexity of this? So how many times will this statement get executed? Whatever is there inside the braces. So when I say time complexity is nothing but it should flash in your mind how many times the statement will get executed. So that is nothing but your time complexity. Okay. So how many times the statement will get executed? Quickly. Right. So it is again O of n, O of n, right? So it is again O of n, right? Okay, so far I think, hope everyone is understanding, right? So now we will take another example, right? A slightly a different example. So I am not incrementing it by 1, I am incrementing it just by 5. So what will be the time complexity of this? So how many times will this statement get executed, and how will you try to derive or represent it in terms of the big O of n? So I've already given you an explanation or given you a disclaimer that coefficients and the constant terms you have to eliminate, right? So if at all you say that it is getting executed, say, so earlier it was n times, and here you say that n by whatever fraction it is, so whatever times, so that 1 divided by, you have to just eliminate, you have to take it out, right? Okay, so in order to express this O of n, see n minus 1, right? So beneath actually n minus 1, so as I said, minus 1 is a constant term, right? So we have to eliminate the constant term or any coefficients with this which is associated with the n term, right? So which is why we are just indicating it with respect to what degree of n is, will this actually vary, right? Okay, so n by 5, right? So n by 5, so again I had already told you that 1 by 5 you can eliminate, so it will again give you O of n, right? So many of you have actually given O of n by 5. Mathematically it is right, it is correct, it will actually try to compute, or it will get executed n by 5 times, no doubt. But that 1 by 5 term you have to eliminate in order to express it in a big O notation, right? Correct. So it will again be O of n. Okay. Okay, so next, so we are actually trying to move ahead with one step bigger, or we are making it a little harder, right? So I've taken two loops now. I've considered two loops. So one loop is there is one outer loop and there is one inner loop, and there is a statement within that inner loop, right? So this is a next nested for loop. So outer for loop I am executing it from 0 to n, and the inner loop also from 0 to n, and there is a statement. So how many times the statement will get executed? How many times will the statement get executed? Right? O of n square. Okay. O of n square. Okay. Right? So how is it O of n square actually? So for each and every time the I value is getting incremented, right? So say from I is equal to 0, if I increment it to 1, again the J for loop is running from 1 to n, right? When I increment it I from 1 to 2, again J is iterating from 1 to n. So how many times this J for loop is I am trying to execute, right? So how many times the inner for loop is getting executed? N times, n times, n times. How many times does that 0 to n is being run? N times again, right? So n multiplied by n will actually give me n square, right? So the statement will ultimately be repetitively executed for n into n, that is nothing but the n square times, right? So for each and every value of I from 0 to 1 or 1 to 2 or 2 to 3, for every iteration of I am running the J loop from 1 to n. Correct? Okay, so hope you're following, guys. N times n, right? So that is nothing but the O of n square. So n multiplied by n will actually give me n square, right? So most of you have given the right answer. That is, it is two loops, and it will actually give me O of n square, right? So it is a nested for loop. That is where you have to actually note down. So now you can see that the degree has actually increased from n to n square. So which means that it will take more time compared to n, O of n, right? Okay. So next, so I have taken again I is equal to 0 to less than or equal to n, and j is equal to 0 to less than or equal to I, and I'm incrementing j. So how many times this statement, inner statement, will get executed, right? So you have to ideally iterate it in your mind, the for loops, right? So when I is equal to 0, my J for loop is running just once, right? J is less than or equal to I. So when my I becomes value 1, how many times will it get executed? My inner for loop 2 times, right? So when I is equal to 3, the inner for loop gets executed 3 times. When I is equal to n, say I have taken 10, n is 10. So when I have reached I is equal to 10, how many times the inner for loop has got executed? 10 times, right? So for each and every value of I am executing this J for loop as many times the value of I, correct? So this will also actually give me O of n square itself, correct? Because during the last iteration, when I have reached I is equal to n, how many times my J for loop also is getting executed? N times itself, correct? So what is the maximum time that it will be taking in that case? Right? So what will be the maximum time? It is again n square itself, right? So during the last iteration of I, when I value is n, right? So n times I have executed the inner for loop J also, the from 0 to I times, that is nothing but the n times. So this will also give me nothing but the O of n square, right? So you have to ultimately, you have to imagine, drawing a table like what will, when I value is this, what will be my J value, and when my I gets incremented, how many times the J also gets executed, right? So here you can see that during the last iteration, when it has reached from 0 to n, your J for loop also has got incremented, or it has increased from 0 to n itself, right? So which is why the time complexity again comes down to O of n square. Okay. So next, taking the next example. So here is a slight modification. So I is equal to 0 to n, no doubt. Here I am taking J is equal to n to I, right? So I have modified the statement from, instead of 0 to I have modified it from n to I. So what will be the time complexity of this code? Yes. Okay, Beneath. So when you say n square plus 2n, no doubt it is a polynomial, I agree. But what is the maximum degree that you have in that polynomial? That is where your big O notation comes into picture. So you have to consider the maximum degree of whatever equation that you have derived. Okay. So n, of course, it is there in the equation, but you cannot express that in the big O notation, right? So big O is nothing but big O. That is where your term actually itself is self-explanatory. That is the maximum degree of whatever the input variable parameter that you have in your equation, right? Okay. Um, yeah, so this also most of you have given it the right answer. It is again O of n square. So if you try to write the table, consider I value, iterating it from 0 to n. And if you try to again consider the j values as well, you can see that you will be iterating it as many times the previous example that we had taken. So it will boil down to O of n square itself. Okay. Okay, so next is, this is very much tricky, I can say. So int p is equal to 0, so 1, 2 less than or equal to p, and I plus plus. So here I am taking a different variable p, and the comparison in the for loop, that is the terminating condition in the for loop, in my for loop is p is less than or equal to n, right? So this is my terminating condition. I am not taking here the iterative variable I am taking the p variable, right? So this is my terminating condition, and p is I am incrementing it every time the I variable is getting incremented. So I'm adding the values of I to the value of p. So it is like cumulative sum, right? So where p is initialized with 0. So as and when I go on incrementing the value of I am cumulatively adding it. So 0 plus 1, 1 plus 2, right? So 0 plus 1 plus 2 plus 3, right? So I'll go on cumulatively adding it, right? Until what condition? p is less than or equal to n, right? So there is some mathematics that is involved here. Okay, you just have to solve in order to get the complexity. Okay. um okay, so solving, actually I have included the steps in my presentation itself. So if at all you want it, I can just open the paint or my whiteboard and try to explain. But as such, there is this uh, the steps itself. If at all, yeah, once the answer is revealed, if at all you don't follow something, then I'll make use of the whiteboard. Okay. O of n plus 1. Okay. So just think of the terminating condition once again, right? So at what will be the value of I when that p is less than or equal to n is achieved? So this is very a little hard, I would say. Yes. So I just included this just to check if you are able to follow it or not. Okay. So as I had said, my sum of p is equal to p plus I. I am cumulatively adding the values of the iterative variable I, right? So when I go on cumulatively adding it, I do not know what will be the value of I when this p will be satisfying the condition of less than or equal to n. So see some k value where your p has reached the value of n, right? So what will be at that instant, what will be the cumulative sum that you will be trying to add? It is nothing but 0 plus 1 plus 2 plus and so on up until k, right? So during the kth iteration or during the ith iteration of k, your cumulative p will be nothing but 0 plus 1 plus 2 up until k, right? Correct. So are you able to follow this? Are you able to follow until here? It's at least. So my terminating condition is not based on I, but instead it is based on p. So once my cumulative sum has reached the value lesser than or equal to n, that is where I stop this loop, right? So what will be the cumulative sum? So say sum at some value of I, my cumulative sum will be up until that iterator variable k, right? Okay. So this you are able to follow, guys. Okay. So you can see that when p reaches n, so n is equal to, so what will be the cumulative sum mathematically? What is the sum of k integers? I had already told you, I had already explained it to you in case of time complexity, right? So what will be the sum of k integers from 0 to k? What is the sum mathematically? How do you express it? It is nothing but k into k plus 1 divided by 2. Correct? Right? So when I have that n is equal to k square plus k divided by 2, ultimately for the iteration, the last iteration, the complexity comes out to be square root of n, right? So that's how you derive until the terminating condition, what will be the condition or what will be the evaluation of the iterator. Based on that, you have to derive the time complexity. Okay, so this actually requires a little bit of mathematics that is involved here. So you have to really jot down or you have to really note, try to prepare a table of the iterator with respect to how the variable also will go on modifying with respect to the values that or the statements that you have. Okay, and then try to derive the complexity with respect to the n. So you have to ultimately express it with respect to the n itself, right? So you cannot express it with respect to any other variable value, right? So it has to be with respect to n, so which is why we have got it as a square root of n. Okay. Okay, so clear on this? So yeah, this is a little advanced of DSA. So this is, where from the basics to the advanced level, everything I have tried to cover. uh, so if at all you have prior knowledge of what is time complexity, also this actually helps. Or if you are even, at once it will be, I agree that at once it will be very difficult to grasp, but within 1.5 hour, whatever I can try to cover from various, beginner or intermediate or expert levels. So all the three levels I've tried to cover within 1.5 hours, so which is why you feel like I am trying to rush through. But yeah, you once you try to practice, you go on solving the problems, or you try to practice the problems again and again, I think you will have a definite, or a rough idea of how to calculate the time complexity. Okay. So multiple, considering multiple examples as well, it is beneficial in order to understanding in a better way. Okay. So again, here I've considered a simple for loop wherein I have taken I is equal to 0, I is less than or equal to n, and here I have multiplied this I with the I into 2. So I have multiplied the iterator with I, multiplication of 2. So I am, not just incrementing the iterator, but I have taken in steps of multiplied by 2. Correct? So I'm executing some sample statement. So what will be the time complexity? So when I say time complexity, you have to jot down the table. So what will be the value of I, right? Until it reaches n, right? So and then how many times this statement gets executed. So that is where you have to, um, yeah, that's how you try to derive. Okay. Okay. So hope you have given a try, right? So as I said, during the first iteration, my value of I is 1, right? So during the next iteration, when I have multiplied it with, okay, so I had to initialize it with 0. So just write down that 0 and just make it 1. Okay. So when I try to multiply it with the, uh, you know, parameter of, um, say I will go on multiplying it with 2 every time. So during my second iteration, it becomes 2 power 1. So during my third iteration, again I am multiplying it by 2. So it will become 2 square, right? So during my fourth iteration, I will again try to multiply that iterator by 2. So that will give me actually 2 cube, right? So during my some random k iteration, what will be the value of the iterator at that instant, wherein it satisfies the condition less than or equal to n. So that will be the terminating condition. So say it will be 2 raised to k, right? So during the last iteration, we would get n is equal to 2 raised to k. So that is when the terminating condition would be achieved, right? So the complexity, if you try to take the logarithmic expression in order to, bring that value k to the base, right? So k is in the exponent term, right? So if you see here, 2, put 2 to the power k. So in order to bring that value k to the base term, or the polynomial expression, you have to take the logarithm, right? So log of n is equal to log of 2 to the power k. So in order to bring that k down, you have to consider the base as 2, right? So that is where you get the k is equal to log of n. Okay. So note that log n is a Ceil value. It is not a floor value. So if at all you try to consider this for loop, okay. So you can note down that it is a Ceil value and it is not a floor value. Okay. Right. Okay. So similar to this, I'll try to take another, another code snippet, right? So I have initialized the value of I as n, and I have tried to go on dividing it by 2. So earlier I was multiplying it by 2. Now I have try to divide it by 2, and then I am checking for the terminating condition I is greater than 0. So I have a statement inside. So what will be the time complexity of this code snippet? Right? Okay. So have you tried to, consider a similar table and try to mathematically compute? Okay, so the table would look something like this. So I have initialized the value of I as n. So during my next iteration, it will be n by 2, right? Because I'm dividing it by 2, right? So during the next iteration, during the third iteration, it will give me n by 4. So that will be the n by 2 square, right? So during fourth iteration, I will further divide it by 2, which will give me n by 8, right? So I can express this as n by 2 cube and so on, right? So during the terminating condition, when I has almost reached 0 during some kth iteration, right? So how can I express this statement as n divided by 2 raised to k, right? So during the kth iteration, when it has satisfied the terminating condition of I greater than 0, I can express that kth iteration as n divided by 2 raised to k, correct? Okay, so when I reaches 1 or it has greater than 0, my I would have reached n divided by 2 raised to k, that is during the kth iteration, right? So for the last iteration, we would get n divided by 2 to the power k is equal to 1. So which gives again the time complexity. So if you bring that 2 raised to k to the right side, again you will get n is equal to 2 to the power k, which is again similar to the previous case, n is equal to 2 to the power k, right? So for in order to again find the complexity, you have to bring that k to the polynomial expression, right? So you try to take the log of n, right? Again the base is 2, so you will get k is equal to log of n, correct? Okay, so this example is just similar to the above statement. You just have to note down what will be the I iteration, right? So how does my I actually look like with respect to each and every iteration, and what will be the base case or what will be the terminating case where this I has actually reached. So above expression, I was reaching the value of n during k iteration, right? So you try to express it accordingly. So here the base case or the terminating cases, I is greater than 0, which means that the last value that it possibly can take is 1, right? And that is where you mathematically try to equate that kth iteration parameter. Okay, so the base case or the terminating case and the iteration, how it tries to grow during each and every loop, is what where you have to try to equate it to. Okay, right? Okay, so this again gives me O of log n. Okay, so next we'll try to see another example. So here I have considered I is equal to 0 and I have taken I square as less than or equal to n. So my base case or the terminating case is nothing but I square is less than or equal to n, right? So terminating case you have to see, and how your iteration is actually growing from one loop to another, next iteration, how that iterator is growing also you have to try to match it. Okay, so my terminating case is I square is less than or equal to n, and I am growing it, incrementing it by steps of 1. Okay, so what will be the time complexity of this? Okay, so this will actually give me I square is equal to n, which means that square root of n. So the loop terminates when I square is equal to n. So ultimately, when I try to fetch what is the value of I, you have to take the square root of n. Correct? I need not even draw a table for this, right? So I is incrementing from 0 to n, no doubt, but the terminating condition really matters, right? So the loop terminates when I square is equal to n, right? So which gives me complexity of square root of n. Okay, clear on this? So this was a little simpler as compared to the previous ones. Okay, so here we try to take another example, so wherein I've taken two independent loops. Okay, so note that it is not a nested loop, but instead it is two independent loops. Okay, so wherein the first loop I'm trying to consider 0 to n and I'm multiplying it by 2. Okay, and the second loop j is equal to 0 to p and I'm again multiplying it by 2, right? But that p is dependent from the first loop. Okay, so the p is evaluated in the above loop, the first loop. Okay, and in the second for loop I just have an this is an independent loop, but the terminating case has the uh, variable p. Okay, right? So so you can just see that we had seen 0 to n multiplying it by 2 will give a complexity of log n, right? So from 0 to n, whenever I am evaluating it in multiples of 2, I will get a complexity of log n, right? So this is independent of the any other variable or any other parameter, right? So my second loop, what is the complexity? It is just similar to the above statement, right? So complexity is nothing but log of p, correct? So log of p is nothing but the terminating condition, right? So I'm trying to express it in terms of the terminating condition. So above one is log of n, and the second statement is log of p. Now p is actually being modified with the above loop, right? So how many times it gets incremented is nothing but that statement is run those many times, right? So how many ever that the above statement runs, those many times my p variable gets incremented during each execution, correct? So since p is evaluated each time the loop is run, so how many times the above loop runs, actually we have got it to be log n, right? So log n times my p variable is evaluated. So can you not substitute that p variable in the below statement, because that is where my dependent variable or a dependent parameter p is there. So even though the loops are independent, right, but the value that you are considering is dependent on where you have actually tried to modify, right? So this will actually give me log of n, correct? So log of p, you know it from the previous statement. Whenever you try to multiply it by 2, your statement also gets executed logarithmic of the p times, right? So log of p times your statement will get executed, but the p also is growing. So how many times will that p grow, or how many times that p statement got executed? It is again log n times, right? So from the above loop, it has computed the p value has computed log n times, and in the below expression I'm using that p in another loop, so which is why I have to substitute in the time complexity parameter as well. Okay, so this will give me actually log of n, right? Okay, right. So here, next case, I have considered two nested loops, right? So my outer for loop is being evaluated from 0 to n, and my inner for loop from 1 to n. Again, I have a multiplying parameter by 2 in the inner for loop, right? So outer for loop is being incremented just by 1, whereas my inner for loop is being incremented or being multiplied by 2. Okay, so what will be the time complexity, or how many times does the inner statement gets executed? See, outer for loop time complexity, you know it very well, right? N times my inner statements will get executed, right? So that time complexity, you know it very well. Now you have to compute the inner time complexity with respect to outer time complexity and try to match it with them. Okay. So most of you are saying n log n. Okay. Okay. So as I said, the outer for loop complexity is O of n, right? So now what is the independent inner time complexity? It is log n, right? So if at all I had just this for loop from 1 to n being multiplied it by twice, so I will have a logarithmic n time complexity, right? So if at all that loop was independent, now I am running it n times, right? So the outer loop is running n times and my inner loop is will also run n times, right? And this n times I am, again, the inner statement is being evaluated with the multiplication of n and log n, right? So this will give me a total time complexity of n multiplied by log n. So, right, most of you have given the right answer. It is nothing but n multiplied by log of n, right? So outer for loop is being executed n times. Inner for loop independently it is getting executed log n times. It will get executed log n times, but it is being repeated repetitively. It is being run n times, right? So it is dependent on the outer for loop. So outer for loop is being run n times. So those many n times I am running again log n times the inner for loop, right? So this will actually give me n multiplied by log n, logarithmic n time complexity. Okay. Okay, so the last question of today's session. So let's see how many of you have understood, really understood, and how many of you can give the right answer for this. Okay, so I've switched the loops. So outer for loop is getting executed. You know, this is just similar to the inner for loop I have considered in the previous example, right? So again, I have time complexity for the outer for loop as log n. I've given you hint, and my inner for loop again will get executed O of n times, right? So independent complexity I have already told you. Now try to compare or try to match it with the dependent or the nested for loops. Considering nested for loops, how many times my inner statement will get executed? Okay, correct. O of n. Okay. O of n log n. O of n, right? N square by 2. Okay. So I'm getting varied answers. So see, my inner loop is dependent on I parameter. So how is I varying? It is varying logarithmically, right? Correct. So when I'm trying to execute the inner statement, it is dependent on I. Correct. My terminating condition is dependent on I parameter and not the n parameter, right? Correct. So in this case, you really have to again put down a table. So during first iteration, I have initialized the I value as n. So my J loop runs from 0 to n, no doubt. Correct. During the second iteration, right, I'm dividing that iterator by 2. That is nothing but n by 2. Correct. Right. So this will actually, I will again be running the inner for loop from 0, 1, 2, 3 up until only n by 2. Correct. And during my next iteration of I am again further dividing it by 2, which gives me n by 4. Right. So during that time, how will the j actually varies, or how many times the j gets executed from 0, 1, 2, 3 up until n by 4. So during my last iteration, what is the terminating condition where the I loop actually stops? That is nothing but 1, right? So when I is equal to 1, what will be the or how many times the j for loop actually runs? So that will nothing but the 0 or 1, right? So it is negligibly smaller as compared to the first time when it has run from 0 to n, isn't it? Correct. So the total number of runs is nothing but n plus n by 2 plus n by 4. So this is again a progressive or a progression, right? So this is a GP series, right? So which you have to try to mathematically try to again compute it, right? So if I take the n parameter out as a const or n as a common parameter out of all these series, so n I will try to take it outside. So I will have 1 plus half plus 1 by 4 plus and so on until a very negligibly small value, correct? So 1 plus 1 by 2 plus 1 by 4 is again a constant term, correct? Right? So 1 plus 1 by 2 plus 1 by 4, they will all lead me to a in getting a constant term. So as I said, the constant or the coefficients, I will just try to have to neglect it. The only variable parameter that will be remaining with me is nothing but the n, right? So the time complexity in this case is nothing but O of n. Okay. So yeah, this was the last question that I had with respect to today's session. Okay. So I have the assignments included here. Okay. I have multiple, I have a couple of, code snippets as an assignment. So the first assignment is I have again nested for loop. Okay. And you just have to find out or calculate the time complexity of this code snippet. Okay. So the second code snippet also I have again a nested for loop. So my for loop, outer for loop is logarithmically increasing and my inner for loop is linearly increasing. So how many times the count is equal to count plus 1 gets executed, right? So these are the two code snippets that I have as an assignment for you. Okay. And third question is try to find the best case, average case, and worst case of the linear search algorithm, right? So you have to know the linear search algorithm for this. Try to find out, try to write down the algorithm first, and then try to derive the best case, average case, and the worst case parameters of this linear search algorithm. Okay. So these are the assignment questions that I have for today. Okay. So please try to solve them. Okay. So we will try to discuss these questions in the tomorrow's session. Okay. So tomorrow is going to be the day 2 session. And yeah. So yeah, please try to at least give a try to give an approach for in solving them, and we will try to see you in the tomorrow's class. Okay. So any questions? I know that this session was quite from the beginner session to an expert level. I have tried to cover various topics. So for beginners, you might feel that okay, this is too much at once. You are not able to digest. But so I would recommend you to go through the presentation. Okay. So please try to go through various code snippets that I've tried to include. Also try to explore it on your own. Try to mathematically express the iterator values with respect to the terminating or the base case that you have for the loops, and manipulate the time complexities accordingly. Okay. So yeah, I think that's all I had for today's session, and thank you everyone for your patient listening. And yeah, so you have been a great audience for me. Okay. And I'll try to come up with the solutions for the assignment questions in the next class. Okay. Okay, then thank you, and have a nice evening, everyone. Okay. And I'll see you tomorrow with the dynamic memory allocation and the linked list concepts. Okay. Yeah, I'll try to circulate the PPT, so it will be there with you in quite some time now. Okay. Okay, then thank you everyone, and then have a nice evening. And yeah, enjoy learning the associated concepts with the time complexity. Okay. And yeah, I'll see you tomorrow with the next concepts. Okay. Okay. Thank you. Bye bye. Bye.